Hello and welcome to another session of Introduction to Engineering and Architecture. Previously, we have discussed several engineering and architecture fields, and although each field is different from the other, we learned that one of the foundations of all fields is mathematics. In this session, we begin our discussion of basic mathematical concepts which you will find useful in your future engineering or architecture interests. Before formally beginning our discussion, here are several photos which surely are familiar to most of us. Some of you might have bumped into these problems or even challenged by some of your friends to solve these problems. People have different ways of dealing with this, from trial and error to wild guessing and to more formal ways. The goal is to find the values of objects given their equivalence when added or operated with other objects. While this may look trivial and informal, we might encounter the same problem in a more formal setting. Take this circuit for instance. In analyzing a circuit, we usually use the Kirchhoff's rules. Let's say you want to determine the currents in this circuit. Using Kirchhoff's rules, you will end up with this setup. Although this looks quite different, the idea is the same. We solve for different variables given a set of equations. In order to solve this systematically, we need to learn systems of linear equations. In this session, we will define systems of linear equations, solve systems of linear equations, and solve real-life problems involving systems of linear equations. We want to begin the discussion by defining linear equations. Linear equations are equations in which the exponent of each variable is 1. For example, 2 plus x equals 3, 3x plus 2y equals 6, or x plus 1 half y equals 4z. Now, what is a system of linear equations? A system of linear equations consists of two or more linear equations. Here is an example of two equations with two unknowns, three equations with three unknowns, and four equations with four unknowns. You might have noticed that the number of equations correspond to the number of unknowns. Let's discuss why this is the case. Take this system. Let us say you're only given one equation and is asked to identify the values of x and y. Now, since there is only one equation, there could be a lot of possible combinations of x and y values, and all of them will satisfy the equation. But when we introduce another equation, it's possible to find only one set of x and y values because both values need to satisfy both of these equations. The question now is, how do we find these values? Again, you can try several methods, but one of the most common methods are substitution and elimination method. In this session, we will solve systems of linear equations using the elimination method. Let's begin with a simple problem. Given x minus 2y equals 1 and 3x plus 2y equals 11, solve for x and y. Elimination method is named as such because you would want to eliminate variables until only one variable is left. This way, you can solve the remaining variable and use this value to solve the other variables. First, let's look for a term that we could eliminate, meaning terms which when added will give us 0. In this case, it would be negative 2y and positive 2y. Combining both equations, we get 4x plus 0 equals 12, or 4x equals 12. Dividing both sides by 4 to solve for x, we get x equals 3. Now that we know the value of x, we can then substitute this value to either x minus 2y equals 1 or 3x plus 2y equals 11. Let's use x minus 2y equals 1. Substituting 3 to x, we get 3 minus 2y equals 1. Then we subtract both sides by 3 and we get negative 2y equals 1 minus 3 or negative 2y equals negative 2. We divide both sides by negative 2 and get y equals 1. We now have solved for the values of x and y. To check, you can substitute these values to the equations and they will satisfy these equations. We now remember what we did to solve the system using elimination method. First, we eliminate a variable. Then, we solve for the other variable. Finally, we substitute the result to either of the equations to solve the remaining variable. Let us use more or less the same method in solving our next problem. In this system, we notice that we cannot readily eliminate a term. Although the coefficients of y in both equations have opposite signs, when they are combined, they do not result to 0. We can, however, manipulate both equations to eliminate a term. I will multiply 2 to equation 1 and multiply 3 to equation 2. You need to first identify what variable you want to eliminate first to know what numbers you will be multiplying to each equation. Also, make sure that you multiply the same number to both sides of the equation to retain its equality. Solving, I will get 4x minus 6y equals 32 for the first equation, and 15x plus 6y equals 6 for the second equation. This is obtained by doing distributive property, that is, multiplying 2 to each term in the first equation and 3 to each term in the second equation. Now, we see that we can eliminate y. Adding both equations, we get 19x equals 38. Dividing both sides by 19, we get x equals 2. Now that we know that x is equal to 2, we can then substitute this to either of the equations. I will use 2x minus 3y equals 16. Substituting, I get 2 times 2 minus 3y equals 16. Simplifying, then subtracting 4 from both sides, I get 3y equals 12. Dividing both sides by 3, I now have the value of y, which is 4. And the system is solved. Let's now have a more complicated problem that involves 3 equations and 3 unknowns. Let us first decide on which of these 3 variables do we want to eliminate first. Although we can select any of them, it would be more strategic to choose that which we anticipate is more convenient. In this case, y. Pick 2 equations that you want to pair up first. Let's choose equation 1 and equation 2. We do what we did in the previous problem. In this case, I will multiply equation 1 by positive 3 so that I can eliminate the second term. This will now give me this system. Again, make sure that you're multiplying the number to each term correctly. We can now eliminate y. Solving, we get 17x plus 17z equals 17. It would be better to simplify the equation. Dividing both sides by 17, we get x plus z equals 1. Now, this is an equation that involves only 2 variables, x and z. I obtained this by pairing up the first and the second equations. I will now obtain another equation that also involves x and z. This I can do by pairing up the first and the third equations. I will do the same technique in eliminating y. First, I multiply equation 1 by negative 2. I use negative since I want the sign of the coefficient of y to be positive, so that when we add it with the coefficient of y in the other equation, we get 0. Solving, we get this system. We eliminate y. We get negative 3x minus 2z equals negative 5. Now, this is another equation that involves only x and z. We then have another system of 2 equations with 2 unknowns. From here, we can eliminate one of the variables to solve for the other. Let's say I want to eliminate x. I can do this by first multiplying the first equation by 3. I get this system. I can now eliminate the first term, giving me z equals negative 2. Since I now know z, I can use substitution to find x. Let's use 3x plus 3z equals 3. Substituting, I get 3x plus 3 times negative 2 equals 3. Simplifying, I get 3x minus 6 equals 3. Adding 6 to both sides, I get 3x equals 9. Then I divide both sides by 3 to get x equals 3. Since I now know the value of z and x, I can now choose from either of these 3 equations to solve for y. Let's use the first equation. Substituting, I get 5 times 3 minus y plus 4 times negative 2 equals 5. Simplifying, we have 15 minus y minus 8 equals 5. Subtracting 15 and adding 8 to both sides, I get negative y equals negative 2. The value of y then is positive 2. We now have the values of x, y, and z, and we have now solved the system.